Okay, so to actually do this lab, right, I'll show you what to do here. The purpose, again, is to, right, to determine the relationship between the net force acting on an object and its acceleration. All right, the net force and the acceleration. So you make a data table. Gotta get a Sharpie here and mess that up. This is gonna be the net force in newtons, or the sum of the forces, and this is gonna be the acceleration in meters per second squared. All right, record the mass. Keep that handy. All right, so I'll put the fridge on here. All right, turn on everything here. Sum of the forces, net force, that means the same thing. So we've got 250 kilograms. All right, 250 kilograms. Then you start applying a force. All right, let's get it a strong enough force here. Let's turn off friction, no friction. All right, so everything's all right. And if you go up with this arrow, it goes up by 50 newtons at a time. So let's say, there we go, 100 newtons of force. Acceleration, 0.40 meters per second squared. 150, we've got 0.60. 200 newtons, we have 0.80. So it's going up linearly for sure. We keep going. We're at 250. It ends up going too fast eventually, so you do have to go kind of quick here. 300 and 1.2, and I'll get one more. 350, and I can guess 1.4. All right, so I don't need the units in favor. So a little bit messy here. Sorry for this, trying to go quick. All right, and he fell off. They're reaching max speed, right? Once the speedometer hits the peak, he falls off, can't help anymore. But we got our raw data recorded here, right? As we applied more force, so we already see F net, or acceleration, is directly proportional to F net, right? The thing we measured was acceleration. That ends up being directly proportional to the net force. So that's good. Now, let's go to Logger Pro. All right. Where are we here? Kind of a wonky setup I got going here. Logger Pro. All right. We're going to start putting in our data here. On the x-axis is going to be the thing we did, which was force. My keyboard is up underneath the screen, so it's kind of wonky. I should say the net force, right? The total force. It's not literally a net, right? It's the meter or force units, newtons. Always name your axes. Don't be lazy. And acceleration. 2 C's, 1 L. When I first started teaching, I'd never written the word acceleration like on a whiteboard or in front of a class. I was like, wait a minute, how do I spell acceleration? You know, or even it had been years since I put it in written it in a lab report or something. You know, it's funny. You know, spell check reliance is trouble, especially for somebody who's always had spelling. Spelling's always never been my strong suit. I was not a good student in those foundational years, kindergarten, first and second grade, where you really kind of get the bug or don't get the bug. All right, so acceleration, A, meters per second squared, done. All right, so acceleration versus force. So now you put in your numbers, 100, hit the down arrow, 150, 200, 250, 300, 350. All right, and we had an acceleration of 0.4, 0.6, 0.8, 1.0, 1.2, and 1.4. Now, when you use the simulation program, I always right-click auto scale from 0. When you use a simulation program, move this down a little bit, make this a little bit smaller for a second. it'll give you a perfect correlation always, because it's using the calculation that we're deriving they use the calculation we're deriving to program the simulation, right? So here you go. All right, so our experimental equation, let's see what I can do here. Experimental equation is acceleration equals mx plus b. Well, m is the slope of the line. It's 0.0040 meters per second squared per Newton times x. Well, x is f net. Let me hide this so you can see it there. It's f net. All right, y-intercept is 0 here, right? No force, no acceleration. Great. All right, so let's take a look at the slope here. Let's analyze the units first. Meters per second squared per Newton. Well, meters per second squared per Newton. Well, what's a Newton? What is a Newton? Well, a Newton, turns out, in scientific base units, is kilogram times meter per second squared. All right, so what you get here, put brackets around stuff, the meters per second squared cancel, and you end up with units of 1 over kilograms on the slope. So the slope appears to be, looks like the inverse of mass, 1 over mass, right? 1 over kilograms, 1 over mass. So, did we use a mass? Yeah, we did. Let's find out what 1 over that is. 1 over 250. 1 divided by 250 is 0.004. And the units on that are inverse kilograms, or 1 over kilograms. Because if you invert the number, you invert the unit as well. So check that out. Slope of the line is 1 over the mass of the object that was being accelerated. So our final equation here becomes, the general equation becomes the acceleration of the object equals the net force divided by the mass of the object, or 1 over m times f net. And when you multiply something like this, f net just goes on top, and it looks like this. And this is called Newton's second law. Right? Look at that. A few minutes, boom, simulation lab done. All right. The real lab we'll do next year in AP Physics C with the cart and pulleys and masses and all kinds of fun stuff. But this is really important. So that's Newton's second law. Now, one thing you should note is sometimes we rearrange this. We multiply both sides with mass, and we do F net equals ma, right? Mass times acceleration. How does that impact what we're doing? Well, in the last unit, F net was always 0, so there was no acceleration, right? 0, if there's no net force, there's no acceleration. The force is all balanced. This unit, the force is going to be unbalanced. If we know how much force is unbalanced, and we know the mass of the object, we can predict what its acceleration is going to be. And then from that, we can figure out stuff like, okay, how far is it going to move? What speed is it going to get to? And so on. So Newton's second law is the boss of kinematics, of motion, right? Forces are balanced, constant velocity. Forces are unbalanced, we have an acceleration. All right? So that's it for the lab. You're going to write this one up. There's the purpose. This is the raw data. I went through it pretty quickly, kind of messy over here. I apologize for that. Recorded the mass that we measured, the mass of the system, plotted it in Logger Pro, so you're going to have to print out the graph, of course. And this is acceleration goes F net over m, or, I probably should have another piece of paper over here, but, often here's a tardy slip from earlier. And of course, I don't know where my marker went. The other way we can write this, right, pull this out. Newton's second law, we can either say A is F net over m, or we multiply both sides by m and we write F net equals ma. All right, they're equivalent. This is mass or inertia. All All right, mass and inertia, believe it or not, are the same thing. Inertia is not momentum. Most people think inertia is momentum. Like, the more inertia something has, the faster it's moving, the more. No, that's false. The more mass something has, the more inertia it has. Inertia is the tendency of something to resist changes in motion. So the bigger this m is, right, the less acceleration you end up with at a given applied force. So that's what inertia is. Mass resists changes in motion. All right, and we always used to do an experiment with this where we push somebody across the room in the rolly chair, right? And it's a lot harder to stop somebody with more mass, even if it's the same speed, right? You push me in a chair versus my daughter in the chair, I'm going to be a lot harder to stop moving at the same speed because my mass is larger, my inertia is larger. All right, inertia has nothing to do with speed, believe it or not. It's just literally it's just the mass of the object. All right, that's it for this one. Have fun with the lab write-up. We do next do Monday. All right, talk to you later. Have a good one. Gotta pause this. Stop sharing.